King of the Hill triathlon race in Kinsale consists of a 750-metre swim, followed by a 20-kilometre cycle, followed by a 5-kilometre run. The questions below are based on data from 224 athletes who completed this triathlon in 2010. Maura is analysing data from the race using statistical software. She has a data file with each competitor's time for each part of the race, along with various other details of the competitors. Maura produces histograms of the times for the 3 events. Here are the 3 histograms. Now, we want to find the event that on average takes longest to complete. So we have to consider the mean of a histogram. Now the mean is the balance point of a histogram. So for example, for the swim, we could imagine that all of these bars are weights on a seesaw. So the seesaw is this horizontal line. And you have to imagine where a balance point might be. Well, I could show the balance point like this. So it's balancing here and this point here. So you can see the mean is obviously somewhere between 14 and 22. Similarly for the cycle, the mean of this histogram looks like it's somewhere between 38 and 46. The mean for the run lies between 20 and 28. We can be confident of that range. So we can see quite clearly that the mean time for the cycle is greater than the mean time for either the swim or the run. We can be confident that the mean time for the cycle is greater than 38 minutes. We don't have to know the exact time, of course. We know it's somewhere between 38 and 46. The balance point has to be somewhere along here, if you think about it. Just by looking at it, we don't have to know the exact mean. But since the mean time is greater than 38, well, clearly this mean time is going to be greater than the mean time for the run, because the mean time for the run has to be less than 28, and the mean time for the swim similarly has to be less than 22. So you can see that the mean time for the cycle is the greatest. In all 3 histograms, the times are grouped into intervals of how many minutes? Well, let's look at this one here. What's the width of each bar? Well, from 22 to 26, that is 2 bars. So the width of 1 bar is 2. So this point here has to be 24. So this bar runs from 22 to 24. The next bar goes from 24 to 26. The next one from 26 to 28, and so on. And you can see it's the same for this histogram here. We have a bar here with a width of 2, 52, this point here which is 52, and next bar has a width running from as a width of 2, goes from 52 to 54. So each bar has a width of 2. So the interval is 2 minutes. You can see that it's the same here, 28 to 30 for this bar here, and then 30 to 32 for the bar next to it. Now we're interested here in the median time for the run. Now the median time is the time that cuts the area of this histogram in 2. It's not the same as the mean. So we have to look at a point along the horizontal axis here, such that when we take that point and use it to cut the area of the histogram into 2 parts, then each part will have the same area. So we want this part here to have the same area as this part here. And if that's the case, then this here is the median time. Now we're only getting this approximately. So I'm going to use this value here that I indicated. It looks like it cuts it in 2 approximately. It looks like a number between 24 and 26. I might write down 25. Yeah, I think I'll just write down 25 for that. It's close enough. To get the exact value, we'd have to get the area under the histogram. We would have to get the heights of each of these bars, get the area of each rectangle by multiplying the height by the width, summing them all and dividing by 2, and then going to the point along the horizontal axis that gives half the area. Now in the next question, we're interested in the event in which the times are most spread out. Well, actually that event is the cycle event, because some people completed the cycle event in times between 30 and 32 minutes. And some people took from 56 to 60 minutes. This pint here is 56. This pint here is 60. So we have a bigger range of times here than we have for the other events. The minimum time for the swim is somewhere between 10 and 12 minutes. The maximum time is between 30 and 32. The minimum for the run is from 16 to 18. The maximum for the run is from 34 to 38 minutes. But here it's from, the minimum is 30 to 32. The maximum is 56 to 60. Maura is interested in the relationship between the athlete's performance in the run and in the cycle. She produces the following scatter diagram. Now, from the first part of the question, if you read it, you will see that there were 224 athletes who took part in this competition. So, for example, this point here in the scatter diagram represents an athlete whose cycle time is given by this value here, whatever it is. It's about 54 minutes, and whose run time is given by this value here, which is a little bit more than 25 minutes. Now we're interested in the correlation coefficient between the times for these two events. Now, just to remind you of what correlation coefficient means again, it's a measure of the linear relationship between two variables. So the two variables in general are y and x. Well, in this case, the variables are run time and cycle time. If the points in the scatter plot happen to lie in a perfect straight line, which is positive slope, that means a line going in this direction. It doesn't matter what the slope is. It could be like this, could be much steeper, but if that line has positive slope and all the points lie on a straight line, then the correlation is +1. You can't get a higher correlation than +1. Of course, that never really happens in practice. It's usually less than +1. If there's no correlation between y and x, then we say that r is 0. The correlation is r. The correlation coefficient is 0. So we just have a random scatter and no linear relationship between y and x. Now, if the linear relationship goes the other way, we have negative correlation. So if the points lie on a perfect straight line and that straight line has negative slope, then we say the correlation is -1. So the correlation coefficient is a number that lies between -1 and +1. So if we look at this diagram here, we see that the correlation coefficient is some positive number. It's not +1, of course, because all these 224 points do not lie in a perfect straight line. That's obvious. But it's still, you can see that there's still a pretty good linear relationship between y and x, or between the run time and the cycle time. Now it's not going to be 0.95 because 0.95 is quite close to +1. 0.77 is more like it. So there's a fairly strong positive correlation between run time and cycle time. 0.95, as I said, is too strong a correlation. In that case, the points would be very close to a straight line. That's not happening. 0.13 is too small. 0.13 is close to 0 actually. So that would be a fairly random scatter with not much of a linear relationship. And D, E, and F you can rule out straight away because these values are negative. For a negative correlation, the data would have to run like this. The data would be running in the opposite direction, from the top left to the bottom right. Frank was the slowest person in the run. How many people took longer to complete the cycle than Frank did? So let's look for the point here which has the longest run time. So the fact that Frank was the slowest person in the run means that his run time was longest. So which point here has longest run time? It looks like this point up here. So the run time here is roughly 37 minutes. It's between 35 and 40, about 37 minutes. His cycle time is amongst the longest as well. His cycle time is about here. It's about 52 or 53 minutes, but it's not the longest. Some people took longer to complete the cycle. So if we look at those points, what we can see is this one, and this one as well, I think, and also this one. So that's 1, 2, 3, 4, 5, 6 people. 6 people had cycle times that are longer than Frank's. Brian did not enter this race. Suppose that he had, and suppose that he completed the cycle in 52 minutes and the run in 18 minutes. Explain why this performance would have been very unusual. So let's look at 52 here. Well, it's roughly midway between 50 and 55. It's about here. So that's cycle time, and a run time of 18 minutes. Well, that's about midway between 15 and 20. Well, midway is 17.5, so it's about here. Now, why would this point be a very unusual point in this scatter diagram? Well, you can see what the overall trend is. As cycle time increases, run time tends to increase on average. That's because we got a fairly strong positive linear correlation. So for this fairly high cycle time of 52 minutes, we would expect a high run time. So to answer this question, you could state the correlation coefficient. You can see that there's a strong positive linear correlation between runtime and cycle time. So for high cycle times, you would expect high run times, and vice versa. If someone has a high run time, you would expect on average that that same person would have a high cycle time. You can also say it the other way around. You could say if the cycle time is low, then you would expect that person to have a low run time. By the way, this makes sense. You know, if a person is fit, then you would expect, you know, well, for the fittest people, for the strongest athletes, you would expect their cycle times to be fairly low compared to the rest. And if that's the case for the cycle time, it's not too surprising that the run time is also low. Maura knows already that the male athletes tend to be slightly faster than the female athletes. She also knows that athletes can get slower as they get older. She thinks that male athletes in their 40s might be about the same as female athletes in their 30s. She decides to draw a back-to-back stem and leaf diagram of the times of these two groups for the swim. There were 28 females in their 30s and 32 males in their 40s. Here's the diagram. So on the right here we have all the males. Well, we have actually got 32 males, and these are the times. So for example, 14.9 here means that we have a male athlete aged between 40 and 49 who took 14.9 minutes for the swim. This value here is the time for a male athlete. It is 18.8 minutes for a swim. So the times are increasing as we go down and across. For the males, for the females, the times are increasing as we go down and go to the left. So for example, we have 1, 2, 3, 4, 5, 6, 7 females who took between 16 and 17 minutes to complete the swim. So this number here represents a female who took 16.2 minutes. Here's another female who took 16.2 minutes, then 16.3, 16.7, and so on. Now, if there was a significant difference between the times for the females and the males, then you would expect less symmetry here. For example, if it was the case that the males take significantly longer than the females, then you would expect a load of values further down this stem and leaf diagram. But you can see that these values here are more or less directly across from most of are nearly all the female values. So that this stem and leaf diagram is roughly symmetrical. Okay, there are a few athletes that took longer than everybody else. There's actually 3 female athletes that took longer than everyone else, but that's only 3 of them. There is one athlete that took the least amount of time. That was a female athlete. That female athlete took 13.4 minutes. These 3 here took longer. One of them took 24.8, another one took 26.5, another one took 29.7 minutes. But the bulk of the times are roughly the same. So we could conclude that there is not any significant difference in the times between female athletes aged 30 to 39 years and male athletes aged 40 to 49 years.